right, welcome back to another video. I'm going to tell you a joke about a jumping rope. Actually, I'm going to skip it. Okay, so today's lesson, we are talking about lines of best fit. And not only that, we're also going to look into this thing called the least squares regression line. Okay, so it's kind of like they're the same, but not the same. So I'll try not to overwhelm you with too much information. So a line of best fit and a least squares regression line, it's a way to approximate the linear relationship between two variables. Okay. So what ends up happening is, I'll give you a little bit of an idea. Here's the difference between the two. Okay. If this is going too fast, you can pause, go back. That's the beauty of a video. But with a line of best fit, it's a lot easier because it's an approximation where you draw by eye. Okay, so that means you kind of see your scatter plot and you kind of draw a line that you think best represents the data. Okay, the only thing you need to really note is when you draw it, you kind of want the same number of data points or dots above and below the line, and I'll show you how we do that. Now, the least squares regression line it does the same thing, but the only difference is we don't draw it by eye. We actually calculate it using our calculator with the stat mode. Okay, now a straight line, this should look familiar. It's kind of in the form y equals mx plus c. But here in the calculator, I've written, it looks y equals bx plus a, or y equals a plus bx. Now this one here, I'm picking this top one because that kind of looks like our straight line formula. We're used to some gradient times x, and then plus your y-intercept. But this bottom one here, some people like to memorize that one because it's alphabetical. So y equals a plus bx. And in your calculators, you'll soon find that you've got a y-intercept. If you kind of press the letter A, or if you use the letter B, you'll get the gradient. So that's where these formulas come from. And again, I'll show you how to use these. It's the exact same process as finding your Pearson's correlation coefficient. So often with a question like this, they'll give you a set of data and then they'll ask you to find Pearson's correlations coefficient, and then they'll also ask you to find the least squares regression line. Okay. Now, to give you an idea of how it's calculated, I've got a question here. Okay. Now it says here we want to find the line of best fit, and we also want to find the least squares regression line. Okay, so for the first part here, for your line of best fit, I'm going to draw it in green. For the line of best fit, we're going to draw this by eye. And I can see that these are my data points, and I'm going to assume it's going to be somewhat roughly, that's close enough for me. Okay. Now this line, to me, looks like it kind of represents my data as close as we can. And I'm also looking here, we've got roughly the same amount of dots up top than we do on the bottom. So we've got 3 top, 3 bottom, and I guess that one kind of goes through. So we're pretty close. That's good enough for us. Okay, there's your line of best fit. Now, that's really it. If we wanted to, we could find the equation of the line of best fit by finding, we could find the gradient. We see that the y-intercept for this one here, we can see that the y-intercept is 100. But we can see here, oops, I changed those colors, but that's fine. And then we can kind of see, I'm going to pick a random piece from our graph. And from here, I can kind of see the rise 25 to 35. Whoop, the run is 10. And the rise from there to there, 135 to 145 is 135 to, it's 10 as well. So that means the gradient here, in this case, the gradient is 10 over 10, rise over run, which also equals to 1. Okay, so if I wanted to, the line of best fit, if you wanted to give it an equation, which you don't have to unless they ask, they'll often just ask you to draw it. But if they want the equation, we can see here that it's y equals to mx plus c, because it's a straight line, but we know that the gradient we said was 1. So I can kind of get rid of that m. The gradient is 1, and then instead of c, or the y-intercept, we can see here that the y-intercept is roughly 100. So that there would be our equation of the line of best fit. Okay, we've done it by eye, and then we've just kind of used our linear relationships kind of stuff to figure that out. Now, if we're using our least squares regression line, The first thing, if we only were given this graph, and I'm going to change these back to red because otherwise it's going to drive me crazy. To find the least squares regression line, we're going to have to use the calculator. Okay, so we're going to find the data points first. I've been nice enough to give you that table here. So basically when x equals to 10, we can see here that the value here is 125. Okay, now just remember again, x is generally your independent variable, and then your y is your dependent variable. So that's where I picked these numbers from, 20 to 125, 25, 130, and so on and so forth. Those are the values there. Okay, and now your calculator, you're going to put it into this mode. It's going to be hard for me to show you, but you'll click mode, then you'll click stat, and then you'll get a whole bunch of options. You'll pick the option that says a plus bx or 2 variables. And then at that point there, what you want to do is you want to input all your data. You want to say it's either this value or like, what is it? You want to put 10 in the X column. And then you want to put 125 in the column next to it. And then you keep going one down. The next X value is 20. And the one below is 125. You fill those out. And then once you've inputted all your data, you press AC, which feels weird. Don't press off, just press AC. And then you'll go shift 1. So you get the stat value. And you'll get a whole bunch of options here. Now, A becomes your y-intercept, B is your gradient, and then we know R is your Pearson's correlation coefficient. We're not going to use that for this, but it's there if you need. So for your least squares regression, I'm going to go with the formula y equals to a plus bx. And so here, once I've put that all in, y is just going to equal to, I'm going to figure out what a is. A is going to be roughly 111 point, I'm going to do it to 1 decimal place, 0.7. And then plus B, and B, I'm going to go back and do the same thing, shift stat 1, REG, and then pick B this time. So, and that will give me 0.9 approximately X. And so this would be the equation of the least squares regression line. So as you can see, they're both fairly close. This one here is 1x, this one here is 0.9x. So 1 and 0.9 fairly close. And this one here looks like 100, but here it's 111. We're fairly close to the ballpark. So they do the same thing. But yeah, we can see that one is calculated in a different way. One's done by eye, and then the other one is done by a calculator. Okay, the last thing that they may ask is they'll ask something roughly about like, tell us what this means in terms of the data, or what the gradient means in terms of the data. So in this case here, if I go with this one 0.9, what it's saying here is that 0.9 equals rise over run. Okay. Now, gradient rise, we're talking about the height. So that means height is up the top, and then time is at the bottom. So what it's saying here is, technically we're saying for every 0.9 is the same thing as 9 over 10. Okay. So I've just kind of rewritten it as 9 over 10 as a fraction. And so what it's saying here, this is the tricky part. It's kind of saying that for every 9 height, I guess, that we go up, we actually run across 10. Yeah. So it shouldn't be h on 10, sorry, it should be h on t. So that means for every, you can talk about for every 10 minutes, we kind of grow in 9 centimeters height, or for every 9 centimeters height that we grow, we're actually taking 10 minutes. So that's kind of what it means to look at it in context, or look at the gradient in terms of the context. Hopefully that helps. Good luck with your exercise, and I'll catch you later. Bye-bye.